Welcome to the online lectures for EEE 447 robotics course. Today's lecture is about computing inverse kinematics. As evident from the name, the problem of inverse kinematics is opposite to that of the forward kinematics. So we will start by revising what we had learned earlier and then move on to formally define inverse kinematics. In this lecture, our focus will be on developing analytical solutions for inverse kinematics problem. We will start the development of the analytical inverse kinematic using two link planar robot example. We will discuss different cases of possible solutions when solving inverse kinematics. We will develop the concept of workspace of a robot. Then we will test our understanding using another example of the spherical robot. We will conclude the lecture with the discussion of the orientation part of the inverse kinematics problem. Inverse kinematics, which as you might guess by the name, is in a way the opposite problem of forward kinematics, which we covered last time. So let's briefly recall what we mean by forward kinematics. Assuming that you have a robot arm, a collection of links and joints, where each joint has a joint value, then the based on those joint values, if you have a base coordinate frame and an end effector coordinate frame, then you can compute the transform from the base to the end effector. So forward kinematics is if someone gives you all the QIs, the angles, all the joint angles, then you can go ahead and compute the transform from the base to the end effector. So this is forward kinematics. And it is not just the end effector. We can compute the transform from the base to every other link and joint. But the one we care about the most is the end effector. So this is forward kinematics. But in the real world, when we are using a robot, for example, we actually care a lot more about the inverse problem. We know where our target object is. So let's say that we would like our end effector to grab that object. Let's draw an object here. Okay, for example, we have an object sitting here like this, and we want our end effector to grab this object. We know the desired transform from the base to the end effector. What we don't know is what are the joint values that our robot must have in order to get to the end effector, to the desired point in space. And that is the inverse kinematics problem. We are given a desired transform from the base to the end effector, and what we have to do is to compute all the joint values that produce this transform. We know we have to get to this point, and we have to compute all the joint values so that the end effector gets to this point. Okay, in this lecture we will be looking at analytical methods for computing the joint values. Later we will also look at numerical options, but for now it's important to start with analytical methods because those will give us some very important insights into the capabilities of robot arms in general. We are going to start with a simple problem in just 2 dimensions, and we are going to do inverse kinematics for the planar 2-link robot, which we have already seen. Okay, let's say we have this table given to us. This is the DH table. And we are given the values for all the DH parameters. I, theta, D, A, and alpha. 1, 2, these are the two joints, Q1, Q2, D1 is 0, D2 is 0. We have 0 0.5 first link, alpha is 0 in both the cases, and this was 0 0.3. So the DH parameters for the planar 2-link robot are given here. We have 2 links and 2 joints. This is evident by these entries. These are 2 joints and these are 2 links. And this is a pretty common way in which you will be seeing problems phrased in this class, that we are given the DH parameters. So first part would be that we have to sketch the robot. Then we have to do the forward kinematics and then compute inverse kinematics. So let's very quickly sketch our robot right here. So I'm going to sketch the corresponding to DH table that we had already seen right here. So this is the base. So it's a 2-link robot. So let me draw the first link. Let's say that this is 0 0.5 and this is my first link. This is my joint, and then we have another link which is smaller. It has a length of 0 0.3, and we can go on and draw our axis here as well. This is the y-axis, this is the x-axis, this is the base coordinate frame. Then we have a coordinate frame attached to the end of link 1 like this, and finally we have the coordinate frame for the end effector attached here. And we can write the joint angles and values. Okay, let's say this is Q1 and this is Q2. This is 0 0.5 and this is 0 0.3. So the first degree of freedom of the joint was this first joint Q1. This was our first degree of freedom. The z-axis, we haven't marked the axis here. Let's mark the axis. This is x0, y0. This is x1, y1, and this is x2, y2. Okay, the z-axis is coming out of the board. So this is first degree of freedom, and this Q2 gives us the second degree of freedom. Okay, let's go ahead and compute the forward kinematics for this robot. Okay, this is the same robot here, and let's go ahead and find the transform. Find the transform from the base to the end effector, and this will be, we know, matrices. The first matrix will correspond to joint 1, and the value for joint is Q1. So cosine of Q1 minus sine of Q1, 0. S1 C1 0 0 0 1. So this is our first matrix. Then we have an identity part for rotation, and the translation along x is 0 0.5, along y is 0, and it's like this. The first row is complete now. Moving on to the second row. Okay, second row we have q2, so cosine of q2 is c2 minus s2, s2 c2 0 0 1 0 0 1, and then we have an identity rotation followed by a translation along x-axis, the local x-axis of 0.3, 0.3. There is no translation along y, and we have this matrix. Okay, so now we can multiply, we can go ahead and multiply the first two matrices and then the second two matrices, and this will give us these transforms. Let me write here: transform from base to the end effector is equal to, the first matrix is C1 minus S1 0.5 C1, S1 C1 0.5 S1 0 0 1, and we multiply it with C2 minus S2 0.3 C1, S2 C2 0.3 S1, and 0 0 1. And remember that we used a few identities. We used the identities to simplify our results. The identities we used were C12 is equal to cosine of Q1 plus Q2 is equal to C1 C2 minus S1 S2. Similarly, another identity that we used was sine of Q1 plus Q2 is equal to S1 C2 plus C1 S2, and this is cosine of Q1 plus Q2, and if it were minus cosine of Q1 minus Q2, then this equation would become written with a positive sign. Similarly, sine of Q1 minus Q2 would be written with a minus sign here. Okay, so this is our forward kinematics, the transform from the base to the end effector. The final form we can write here: transform from the base to the end effector is equal to, multiplying the above mentioned two equations, we get C12 minus S12 0.5 C1 plus 0.3 C12. Then we have S12 C12 0.5 0.5 S1 plus 0.3 S12 and 0 0 1. Pardon, this is a 0 here, 0 0 1. So this is the final transform forward that we had already seen previously, which gives us the transformation from the base of the robot to the tip of the robot or the end effector. Okay, so this is our starting point for computing inverse kinematics. Let's assume that we want our end effector to be at this point in space. So it will have coordinates a and b. Let's draw these coordinates. Okay, so we will have coordinates a and b, and what we are going to do quite a bit in this part of the course is to look at position only inverse kinematics. So we are not going to care about the orientation of the end effector. Let's say that for the moment, the orientation does not matter. The end effector is just a point that we want to be at a given position AB in space. We want our end effector to be at a point represented by AB, this point in space at any given moment. So how can we achieve that? Well, it obviously means that the translation part of our forward kinematics, this is the translation part of our forward kinematics, this has to match with our points A and B. Okay, so in other words, what we have is that if we look at the x component here, this has to be equal to A, and if we look at the y component, this has to be equal to B. So basically we have two equations, that is 0.5 C1 plus 0.3 C12. This should be equal to A, and 0.3 S1 plus 0.5 S12. This would have to be equal to B. Only then we can say that our end effector would be positioned on this point if these two conditions are satisfied. We are not talking about the orientation of the end effector. We just assume that end effector is just a point, and we want our end effector to reach to this point. And to make this possible, these two equations, we need to solve these two equations.